I'm a postdoc at University of Cape Town, and I'm also a part of HIREC's upcoming mission, which is a basically radio telescope array. They are being built in South Africa. So, but today, my goal is to explain these three particular objects. One is Super Chandrasekhar white dwarf, one is fast radio bursts, and the third one is white dwarf pulsars. So let me go one by one. First, in the Super Chandrasekhar, basically, and Howell et al. In 2006, they have observed something very unique, very overluminous type 1a supernova, and its nickel mass content is much higher than the conventional Foucault limit. And from there, they have predicted that this white dwarf, this type 1a supernova has to be originated from white dwarf, which is much higher than the Chandrasekhar mass limit. Even after that, not only this, like 15 or 16 such overluminous type 1a supernovae have been observed over the years. And the predicted white dwarf mass range for all those type 1a supernovae has to be, of this range. And after that, people have given lots of theories, like many theories people have proposed. But which theory is correct, we don't know. The reason is we haven't detected them yet directly. These numbers are quite indirect evidence from the luminosity observation. And so why they are important? Because you can see, we know because Phillips relation is used to understand the standard candle in white dwarfs, but you can see these white dwarfs clearly violate the standard Phillips relation. Not only them, there are many other type 1 supernova have been observed, which actually violate the this one. But yeah, this might say affect the standard candle, but we don't know. Next, let me go through quickly the first radio bursts. First radio bursts are observed in radio wavelength. They are radio transients observed for a millisecond duration, and it's very bright. Basically, they are of the order of Jansky, and they are found to be, some of them found to be repeaters, some of them to be apparently non-repeaters so far, because many FRBs have been detected. They are sometimes seems to be repeating. Some of them have apparently non-repeating. And most of them have been confirmed to be extra-galactic in origin because of their high dispersion measure, but except one of this, which has been recently detected by CHIME. And of course, many of them have, like nearly 600 to 700 FRBs have been detected, and most of them have been detected by CHIME radio telescopes. So what are how FRBs are formed? So people have proposed different theories incorporating these various type of compact objects. And many of these objects, basically many of these theories incorporate merger objects. And the third object I want to point out is the white dwarf pulsar. For example, I'm just telling just one of them, like AIRSCO, and its mass have been proposed to be say around 0.8 to 1.3 solar mass. So basically you have seen basically three particular shortcomings so far. One is that Super Chandrasekhar white dwarf have not been observed directly. And the progenitor theory of the FRBs are not known. Which one is the correct one, we cannot single out so far. And masses of some white dwarf pulsar is also uncertain. Basically, they give some range. So how to understand this? And I'll show that gravitational wave detection in the future can explain all these three quite self-consistently. And what is gravitational waves? You know that any system which has time-varying non-zero quadrupolar moment can emit gravitational radiation. And so far, LIGO Virgo have detected a lot of such gravitational waves from the merger events, and many interesting objects have been detected over the years. And in the future, LIGO Virgo is being still upgraded, and space-based mission like LISA will be launched. And I don't know why this image is such, because I wanted to show basically, okay, this one I can directly come here. Basically, you have a compact object here. And as you remember, I want to get a non-zero quadrupolar moment. So suppose I have an object here, its rotating axis is this direction and magnetic axis in a different direction. So basically it's a pulsar. So if some pulsar is there, we know pulsar emits electromagnetic radiation, but pulsar, because it has this angle chi, basically there is a misalignment between these two axes, they can also emit gravitational radiation. And if you see, these are basically the two modes of gravitational waves which can be emitted by this compact object. And you can see if the object is rotating, say at 1 Hertz frequency, you can see its gravitational wave is emitted at two frequencies. One is 1 Hertz, one is twice of that. And which one is dominating depends on this angle chi. You can see here. And of course, this gravitational wave radiation is not symmetric, because you can see I is checking here, I is the basically detection angle. So once I is varying, so in the basically on all this direction, amount of gravitational waves is emitted are different. So because we need rotation and magnetic field axis of any compact object, let me just go through very quickly. We know rotation can increase the mass of an object, and in very early, people have already shown that it can increase the mass of the white dwarf around 1.8 solar mass. And also, like rotation, because of the centrifugal force, it can deform the shape of the object. And what about for the magnetic field? Magnetic field, because it has different types of magnetic fields. Suppose you have colloidal fields, that means magnetic field lines are in this direction. So effectively, field pressure is more in this direction, so it will make the object kind of this oblate shape. But if it has a toroidal field, that means the magnetic field lines are like this, like torus shape. So the extra pressure will be from the equatorial direction, and then the shape is completely different than these things. So rotation and magnetic field can change the structure of the object, and if they are misaligned to each other, so effectively there is a triaxial symmetry, basically breaking of the axis symmetry, and such an object can actually emit gravitational radiation. And to run all this code, to get the structure, we use a code called XNS code. And the advantage is that you can use all this kind of different field configuration with uniform and differential rotation to get the structure of the object. This code was initially written for neutron star, but we have modified for white dwarf also. So you can see whatever be the magnetic field configuration, once you increase the magnetic field strength, it can increase the mass of the object. And mass of the white dwarf is basically shown here. And because this is a pulsar, because it's emitting pulsar, it can emit gravitational radiation, but because it's a pulsar, it can also emit dipole radiation, electromagnetic dipole radiation that we generally see in radios for neutron star pulsars. So effectively, you need basically dipole luminosity as well as gravitational wave luminosity. An important factor is the omega power 4 here. Basically, it's going as in this omega 4, whereas gravitational wave luminosity goes as omega power 6. So the total energy emitted per unit time, which is the luminosity, has to be contributed from both of these contributions. So once you substitute all these things, you can get the energy conservation and the angular momentum conservation equation. So you can see, basically we have two equations, two unknown variables. Basically, one is how omega, basically angular rotation speed of the object changes with time. Another is the angle, how the axis between the rotation and magnetic field axis changes with time. So you need to solve these two equations simultaneously to get the time variation of this basically objects. Also, to get the signal to noise ratio of the gravitational wave detector, as I have shown, because it's emitting at two frequencies, you need effectively two, it's basically the effective signal to noise ratio is the superposition of the two components, and you can see signal to noise ratio increases with the increase in time. So let's now go by one. For example, if I have a colloidal magnetic field means you have high surface field, so it has high dipole luminosity, so energy loses pretty quickly. In such a scenario, you can see basically if I take a very high dipole field, basically this, whatever basically above this orange line, which is signal to noise ratio is 5, they can be detected. So this can be detected by these two detectors. But if it's low, then again it's different. However, if it's toroidal field, you can see here, then even LISA can detect such a white dwarf within 1 year of observation period. You can see this, but if that's toroidal field, basically it is the maximum field at the center. So if it's low, then again LISA cannot detect it within 1 year. Let me go through one very quickly example of fast radio burst mechanism, which is called Garsten-Zeldovich effect, which basically says that you have an infall gravitational waves, and part of this infall gravitational energy has been converted to electromagnetic radiation because of the basically because of the presence of the magnetic field, and basically this effect is called this GG effect. And the outgoing gravitational wave radiation is the superposition of the, basically the frequency superposition of the infall gravitational waves and the rotation frequency of this object. So effectively you can get the flux, which is basically an object property for the FRBs, you can get. Now once you get all this formulae, you can take some examples. For example, I'm taking this particular FRB, and because these FRBs have this observed property, you can get the light cylinder radius. Basically, light cylinder radius is the time taken by this crossing this wave, and from here you can get the rotation period of this object, and from here you can get the basically magnetic field strength at the surface of this object. And this strength is possible by both white dwarf as well as neutron star. So you can see again here If it's a white dwarf, basically this object is a white dwarf, then we can detect this object. If it's a neutron star, these detectors cannot detect. Similarly, for the white dwarf pulsar, if it's a different this mass, then for example, this detector can detect, but if the white dwarf pulsar has this mass, then no detectors can detect. So in summary, I just want to mention that magnetic fields and rotation can explain the existence of the super Chandrasekhar white dwarf. And if gravitational waves can detect this in the future, we can get basically we can basically restrict the various theories of gravity that people have proposed. And through gravitational waves, we can also better understand the physics of like white dwarf pulsars and FRBs. And of course, there is the important point that LISA can only detect like very highly magnetized central, basically central field should be high. Doesn't matter of the surface field within 1 year of detection period if they reside in within 100 parsec radius. So thank you. These are the references.
Thank you. Questions? Valeria?
Thank you for the very interesting talk. Perhaps I missed it, but what are the frequencies or gravitational wave frequencies of your sources?
Of these white dwarfs, you are saying? For white dwarfs, it has to, if it's isolated spinning white dwarf, it has to be less than 1 Hertz frequency because its size is big. For neutron stars, my size is small, so it goes on the LIGO frequency.
So this is why LISA is...
It's LISA side, yeah.
Okay, thank you.
Another question? I have a more basic question maybe. You are considering a center dipole for a magnetic field. For most of white dwarfs, as far as I know, the magnetic field is decenter, so it's displaced from the center of the star. Is that, you consider that? You think that will affect the results? No?
Yes, basically, if you see the toroidal field, you can see the maximum field is not at the center. It's slightly off-centered. Okay. Yeah. So we basically, this code automatically takes care of this particular effect.
Okay, so you consider
yes.
Yes. Okay. Okay, well, we thank again our speaker and all the speakers from this part of the session.